Ever played with Lego blocks? Imagine now trying to build every number in the universe with just a few special pieces. Sounds impossible? Not in math. These special pieces are called prime numbers like 2, 3, 5, and 7. And here's the fascinating part. You can build every composite number using just these primes, and you'll always build them the same way. No repeats. No mix-ups. That's the magic of the Fundamental Theorem of Arithmetic, one of math's most powerful secrets. Ready to break it down, block by block? Let's dive in. Let's bring this idea to life with an example straight from your textbook. Take the number 32,760. Sounds big, right? But with a simple prime factor tree, we can break it down step by step. 2 times, 2 times, 2 times, 3 times, 3 times, 5 times, 7 times, 13. Now let's express that using powers. That's to raise to the power 3 times 3 squared times 5 times 7 times 13. Here's what's amazing. No matter how you factor this number, you will always arrive at the same set of prime factors with the same powers. That's not a coincidence. That's mathematical law. And it brings us to the powerful principle behind it all, the Fundamental Theorem of Arithmetic. Here comes the heart of it all, the Fundamental Theorem of Arithmetic. It states every composite number can be expressed as a product of prime numbers, and this factorization is unique except for the order of the factors. Let's decode that with a quick example. Take the number 140. You can break it down as 2 times, 2 times, 5 times, 7, or, in exponential form, 2 squared times 5 times 7. Now, whether you started by dividing it by 2 or tried 7 first, it doesn't matter. You'll always end up with the same prime building blocks in the same powers. That's the beauty of this theorem. It guarantees a unique prime fingerprint for every composite number. Let's make this even simpler. Imagine you're building a wall using bricks. The bricks? They're your prime numbers. The wall? That's your final number. Now, whether you stack those bricks left to right or right to left, the wall stays the same. What matters is what bricks you used, not the order you placed them in. Just like in language we have an alphabet to form every word, in math, we use prime numbers to form every composite number. For example, the number 253 is made using just two primes, 11 and 23. That's it, 253 equals 11 multiplied by 23, clean, simple, and unique. Let's put the theorem to the test with a fresh number, 5005. Step 1. Start with the smallest prime that divides it. 5005 divided by 5 equals 1001. Step 2. Now divide 1001 by 7. That gives us 143. Step 3. Next, 143 divided by 11 equals 13. Step 4. And finally, 13 divided by 13 equals 1. We are done. So, the prime factorization of 5005 is 5 multiplied by 7 multiplied by 11 multiplied by 13. A unique combination of primes, just as the fundamental theorem promises. Now let's see how prime factorization helps us practically by finding the HCF and LCM of two numbers. Let's pick 6 and 20. First, break them into primes. 6 is 2 times 3. 20 is 2 squared times 5. To find the HCF, or highest common factor, take the smallest powers of the common primes. They both have the prime 2, and the smallest power is just 2 to the power 1, which is 2. For the LCM, least common multiple, we use the highest powers of all primes involved, that's 2 squared times 3 times 5, which equals 60. And here's a fun check. HCF times LCM gives you 2 times 60 equals 120. And 6 times 20 is also 120. This identity always works, and it's rooted in the power of prime factorization. Here's something cool. The fundamental theorem of arithmetic doesn't just help with factors. It also helps you predict how a decimal number behaves. Here's the trick. If the denominator of a rational number has only 2's and 5's in its prime factorization, the decimal will terminate, it ends. But if the denominator includes any other prime, like 3 or 7, the decimal becomes non-terminating but repeating. Let's try it. 3 divided by 8, the denominator is 2 cubed. So, it terminates as 0.375. Now 4 divided by 7, the denominator is just 7, which is neither 2 nor 5. So, the result is repeating 0.571428, and the pattern goes on forever. All of this thanks to prime factorization. So now you know, every composite number carries a unique prime signature. Whether you're breaking numbers down, solving for HCF and LCM, spotting decimal patterns, or even proving a number is irrational, the fundamental theorem of arithmetic is your go-to tool. It's like having a Mac detective kit, and primes are your clues. In the next video, we'll use this very theorem to unlock one of math's big mysteries, proving that the square root of 2 is irrational. So, stay curious and keep exploring the hidden structure of numbers.